today we are having a presentation about verifiable delay function and groups of unknown order. There will be two presenters, Kelly Olson and Mary Mahler. So Kelly works at Supranational, which is a company which is focused on the hardware acceleration of novel cryptography, and recently worked on the development of software and custom silicon for high-performance zero-knowledge proof and verifiable delay functions. Mary Mahler is a cryptographer specialized in public key cryptography and zero-knowledge proof, and she is now a cryptography researcher at the Ethereum Foundation. So Kelly will start to present, then we'll have some questions on the first part, and then Mary will make a second part of the presentation and another Q&A session. So Kelly, the floor is yours.
Thanks for that introduction, Mark. And just to reiterate for everyone, today I'm going to be talking about verifiable delay functions, which are an exciting new cryptographic primitive. And just to give a brief bit of an introduction, a lot of this work that is being presented is part of an effort by the VDF Alliance. And the VDF Alliance is a collection of academic, nonprofit, and corporate collaborators that are basically trying to bring verifiable delay functions into production and doing it in an open source and collaborative manner. And if you're interested in anything that's happening, in this talk, I would encourage you to check out the VDF Alliance YouTube page. There's a number of great videos there. Or furthermore, there's also vdfresearch.org, where there are basically dozens of papers on groups of unknown order and verifiable delay functions. So to start today, I'm going to give a brief background on groups of unknown order and verifiable delay functions. And then Mary will walk through a little bit more of the technical details, in particular about groups of unknown order and how to construct these in a secure and efficient manner. So just to start with sort of the why and what, a group of unknown order at a sort of very high level is basically a group where the number of elements in the set is not known. And this is, a bit of a technical detail, but really the key here is that these groups of unknown order can be used to construct a wide variety of useful cryptographic primitives, like verifiable delay functions. And really the key here is that having this unknown order ensures that all of the proofs and various higher level cryptographic constructions that are made out of these groups of unknown order, it ensures that they're secure and that you can generate sort of valid proofs that can be verified by folks, and that these false proofs can't be created. And just as an example, there's a wide variety of different groups of unknown order that can be constructed. These can be constructed out of sort of traditional RSA groups that are used for RSA cryptography, or they can be constructed out of more novel types of cryptographic groups, things like class group, hyperelliptic curves, and others. And Mary will give a little bit more detail on groups of unknown order and some of the processes to create these. One of the key things maybe to know about groups of unknown order is that some of them do require a trusted setup process. So for those that are familiar with snarks or zero knowledge proofs, in a very similar way that many of those need to be instantiated with a multi-party computation, the same is true for some types of groups of unknown order. And that will really be the focus of the second part of today's conversation. So to give an example of some of these various use cases, you have things like anti-spam, for blockchain, communication networks. You have things like anti-front running that can be built for decentralized exchange protocols. One of the most interesting use cases is related to on-chain randomness and strong on-chain randomness, either for things like lotteries or maybe leader election and consensus protocols. And then, these groups of unknown order can also be used to construct a wide variety of other really interesting other use cases, things like vector commitments or accumulators, time lock puzzles, proofs of space-time, and there are even sort of snark and second layer protocols like ZK rollups that can be constructed out of these underlying groups of unknown order. So while there are these, sort of wide ecosystem of different use cases, today we're really going to be focusing just on verifiable delay functions in particular. But once again, I would encourage you, if you're interested about, really any of these different use cases or the underlying cryptographic assumptions or cryptographic constructions that enable these use cases, please visit vdfresearch.org, and you'll find that there are a number of presentations and papers on each of these topics. Okay, so just to start with verifiable delay functions and give a very high-level overview, a verifiable delay function is a function that requires a specified number of sequential steps to evaluate the function, and it produces a unique output that can be efficiently verified. So sort of the key components of a VDF and what makes a VDF are really here in this V, the D, and the F. So it's a function, it can be efficiently verified, and the other key is that it requires a number of sequential steps that can't be parallelized. And this is really the way that the delay is introduced in the verifiable delay function. And we'll talk a little bit about what these delay functions are. But really the key here is for decentralized protocols like blockchains, these are sort of a way to introduce a delay, which can then be used to harden the randomness generation process or to prevent front running and many other things. So just to give a brief background on where it's being used, VDFs are actually used in production today. Probably the main example is the recently launched Chia blockchain. VDFs are a part of the proof in space-time consensus in that blockchain. And in that instantiation, they use class group VDFs, but there are a number of other new VDF constructions that are available to use in blockchains today. So as an example, Starkware makes a Stark-based VDF that can be used in Ethereum smart contracts. Filecoin is looking at augmenting their proofs of space to use VDFs, and many other blockchains are looking at VDFs as well, in particular for this randomness beacon and stronger randomness use case. And then maybe just as a piece that's relevant to the Tezos community, this is even something that was suggested a few years ago by Arthur Brightman in a blog post where he suggested that a VDF is one way to sort of delay the generation of the random seed in the Tezos protocol, thereby strengthening the leader election process and the various roles that are assigned as part of the Tezos consensus protocol. So to give a very sort of high level introduction to a VDF, as mentioned before, a VDF is basically just a set of sequential steps that can't be parallelized, and at the end you get an output that someone can check very quickly. So one of the VDFs that we'll be talking about today is an RSA based VDF, and in this VDF, that sequential function is just squaring a 2000-bit number repeatedly. So you have sort of the core function here, which is taking a 2000-bit number and doing a modular squaring on it. And this modulus is really part of in the modulus that is used is really what makes this a group of unknown order, which we'll talk about later. But to enforce this delay, you basically just require someone that's computing the VDF or evaluating the VDF to do these sequential squarings. And as far as we know, if the modulus is of unknown factorization, there's no way to speed this process up other than just doing it completely sequentially. So the way that this VDF works is you have some sort of input that goes into the VDF, and then you have a time parameter, which is how many sequential steps that somebody has to do before they compute the VDF. So one sort of key thing here to recognize is that at the end of the day, a verifiable delay function is really only correlated to sort of the real world wall clock time, insofar as you can estimate how quickly it takes to do a single squaring, right? So if someone is let's say on a 5 gigahertz processor, they're going to do this sequential squaring operations perhaps 5 times faster than someone's that is on a 1 gigahertz processor. And so as you try to construct a secure VDF, you need to make some assumptions about how fast the sort of fastest possible could go, or an attacker could go in the case of a decentralized protocol, and ensure that even if they're operating at that sort of maximum speed, that you're still enforcing some minimum level of delay on them to make the protocol secure. So just to give a sort of high level graphical explanation of how this works is that there's sort of 2 inputs into a verifiable delay function. You provide some sort of pseudo randomness seed into the verifiable delay function. as well as a difficulty, which is basically the number of sequential steps that the user is required to compute. So in this case, you'll provide some random seed. You'll do these 2,000-bit modular squarings repeatedly over and over again, sometimes billions or trillions of times. And then that will produce an output, a single 2,000-bit number. And the other thing that you can also do is create a proof that enables someone to verify that this output really is the correct evaluation of after doing those billions or trillions of steps without having to recreate all of those steps. So a very sort of naive or prototype verifiable delay function is just have someone to do a whole bunch of sequential hashes. And of course, that can be verified, by anyone by just redoing all of those hashes. But really the unique part about a VDF versus some of these other, sort of traditional delay functions or proofs of sequential work is that you get this small and very efficiently verifiable proof that even if it takes you, let's say, 1 day or 1 month to create or evaluate this verifiable delay function, someone can verify that in something like a millisecond. So that's an example of a verifiable delay function. And so the few things that I guess we'll chat about today, I'll cover the first two, is that there are really 3 components to having a successful VDF and bringing a VDF into production. The first one is that you need to make the VDF evaluation fast. So you don't want a large delta between your average user and the fastest that an attacker can go. You really want it to be more egalitarian because this provides some security and some user experience benefits for the verifiable delay function. So that's the first one, is doing that modular squaring and evaluating the VDF very quickly is important for security and user experience benefits. The second is that once you've evaluated this function, you need to make it very easy for people to consume. And so that means that you generate a VDF proof. And there's a variety of different VDF proofs constructions, but the 2 most popular are one created by Benjamin Wesolowski and one created by Krzysztof Pierczek. And these proofs are basically very small and very efficiently verifiable proofs that the evaluation was done correctly. And you want these proofs not only to be able to be efficiently verified, but they also can't be too onerous to create. So those that are familiar with some of other cryptographic proofs like zero knowledge proofs or snarks know that sometimes these can be quite computationally expensive to produce. And so one of the components of a successful VDF system is actually accelerating the proof generation process as well. And then the last one is assuming that you sort of have the basics on the evaluation and the proof generation done quickly and securely, is you really need to make sure that the underlying cryptographic primitives are sound. And this means, understanding the characteristics of the various groups that you're using, whether those be RSA groups or class groups, and that you've really constructed that group of unknown order correctly. And again, the key here is if this group of unknown order is not constructed correctly, then these higher level cryptographic schemes are not going to be secure, and therefore you won't be able to get these benefits like stronger randomness or anti-front running properties, because folks will effectively be able to skip over all of these sequential steps that the VDF is really meant to enforce. So just to talk briefly about why fast VDFs are important and some of the progress that we've made in this. As I mentioned before, the whole point of a verifiable delay function is at the end of the day that you're enforcing a real wall clock delay, right? And so that could be that you want to ensure that maybe someone has waited 1 minute or 1 hour before being able to basically see the output of this delay function. And really the key here is that you're going to have a difference between an average user who in this analogy is traveling at 10 miles an hour, and someone with perhaps a supercomputer or an overclocked computer, or maybe even a custom silicon like an ASIC, who may be able to travel 10, 100, 1,000 times faster than your average user. And so from a usability perspective, what this really means is that if an attacker is 5 times or 10 times faster than the average user, then if you want to enforce a delay of, say, 1 minute, then the average user is going to have to compute that VDF for 5 to 10 minutes. And this is a ratio between the average user and an assumed attacker speed that we refer to as a max or an attacker max. And very simply, in this simple analogy, if the attacker is going 50 miles an hour or 50 computations per second, and the average user is doing 10 computations per second, then this a max number is 5. And so really, the reason that we want to speed up the VDF evaluation process for the average user is to shrink this a max number. And the key is that, given a certain a max, we either have to run, a max number of these VDFs in parallel, or we're only going to get VDFs less frequently. And so really the goal of hardware accelerating the evaluation function is that you get faster time to randomness. So you don't have that multiplier of 5 or 10 or 20x. You get more frequent randomness for the same cost because your evaluator or your computer is spending less time processing the VDF. And then therefore that means you have lower system cost and less energy consumption. And really that's one of the key benefits of VDFs is that they provide strong randomness properties, similar to like a proof of work type protocol, but with much, much less energy consumption. You only need to maybe run, one of these things or a handful of these VDF evaluations rather than data centers full of mining hardware. Okay, so I'm going to just spend maybe about 5 minutes just talking about some of the progress that has been made on the VDF evaluation and the VDF proving improvements before handing it off to Mary to talk more about groups of unknown order and how we actually construct these underlying groups. So on the VDF evaluation, there's been a lot of improvements that have been made by contributors to the VDF Alliance, and they really land in 2 main areas. So the first one is related to algorithms. So as we mentioned in the RSA-based VDFs, we're looking at modular squaring. And while that may seem like just a single operation, it is something that can be parallelized as you get down into sort of the hardware architecture level. And so one of the novel pieces of research that came out of the Activities Alliance was actually a new algorithm that has sort of a log n circuit depth that sort of enables you to do this faster modular squaring. So that's one of the sort of key discoveries that came about in sort of like the last year and a half or so, is a new modular squaring algorithm that's specifically designed for low latency, which is generally not a standard sort of target, I guess, for hardware optimization. Generally, throughput is more likely target. And then the second thing is taking these efficient algorithms and implementing those on various platforms that may provide speed ups. So one of the things that the VDF Alliance has done is implemented this in a CPU using custom assembly code, implemented it on an FPGA, and then also designed an algorithm and implementation that could eventually be manufactured as an ASIC or a piece of custom silicon. So just to give you a very high level idea of what this sort of hardware architecture looks like, is that there is a parameterized squaring unit where basically you have a large amount of multipliers that happen in the silicon, whether that be in the FPGA or the ASIC. You then have a large amount of compressor trees that then reduce these independent multiplications into a single answer. And this design, which has been open sourced, is quite interesting because it can be configured to various sizes, anywhere from 256-bit moduluses all the way up to 4,000-bit moduluses, which enable this design to be used not only for RSA VDFs, but also possibly other VDFs like SNARK-based VDFs. It has very high performance. So we're looking at something like less than 5 nanoseconds per modular squaring. And then it's got a hierarchical design, which means that as you're actually doing performance simulations, you can do this in a way that's much more performant and enables you to sort of rapidly iterate over that. So, what is the net effect of this? Is that we were able to reduce increase the speed and thereby reduce the A max of the VDF from 5,000 down to about 25. And so this is a massive performance improvement. Just to give you some rough numbers, on a CPU, doing a 2,000-bit modular squaring takes about on the order of, I think, around 1,500 or 2,000 nanoseconds. We were able to implement this on an FPGA and get which are quite well work quite well for low latency applications, and get this down to around 60 or 70 nanoseconds. And with the ASIC design, we're expected to get this down closer into that 5 nanosecond range that we talked about. And what this ultimately means is that through this hardware optimization, if you're able to make these ASICs widely available, or the FPGAs widely available, basically you are able to get randomness 200 times sooner than you would be if you were just running on a CPU, or you can be running 200 less instances of the verifiable delay function in order to get randomness as frequently. And if you're interested in learning more about either of these topics, there's a good write-up on the actual hardware algorithm on medium.com/supranational. And there's also a great presentation by Simon Peffers at the Stanford Blockchain Conference. And I believe both of these can be accessed through the vdfresearch.org page. So that's kind of covers the high level about the progress of the Alliance in terms of speeding up the VDF evaluation. Overall, about a 200x performance improvement as you look at the difference between sort of a implementation on a modern CPU versus custom silicon. So the next thing to talk about is VDF proving, and this is generating the verifiable delay function proof that is efficiently verifiable and ideally quite compact, so something like less than a kilobyte. Again, this is really important because we want this to be as accessible and use as little compute power as possible. And so, as we mentioned before, sort of the two key things here to speed this up are algorithms. And so in the case of our activities, we're using an algorithm developed by Benjamin Wesolowski, who created one of the original VDFs, and then it was later enhanced by a company called Argonne Design, who provided some improvements that make it more amenable to parallel architectures. And then we ultimately implemented this algorithm on both the CPU and GPU platforms. And kind of one of the very interesting things that came out of this research was that we've sort of discovered that these GPU platforms are quite amenable to high throughput cryptographic operations. And so in this case, we were able to get something like a 30 to 40x improvement from going from a sort of modern 4-core type processor to a modern graphics card. And so this is really sort of crucial work, because fundamentally this VDF proving is basically a whole bunch of parallel modular multiplication operations. And what this means is that many of these learnings that we discovered as part of the proving hardware acceleration are going to be applicable to other things like zero knowledge proof generation. And so this is a really exciting development for us, because it means that it may make it feasible to generate zero knowledge proofs, say, that are 40 times more complex than folks have been doing on their laptops or desktops today. Okay, so just to talk maybe briefly about some of the future plans and give a bit of a roadmap before I pass it off to Mary. Again, the goal of the VDF Alliance is to develop a fast and secure open source VDF system. And so we sort of have 3 more things that we're going to be working on, in addition to some of the groups of unknown order research that Mary's conducting. The first is that we'll be completing the full chip design of the VDF. So earlier I showed you sort of a graphic that shows sort of the core logical building block, this modular squaring unit, but there are all sorts of other things that need to happen to get a completed chip. And so these are things like integration of various other IPs, like some memory, maybe a USB connection or a PCIe connection, a clock to sort of gate the speed of the chip. So that's one thing that's currently in process, is sort of rounding out the complete ASIC design. The second thing that we're evaluating is, as I mentioned, there's a variety of different constructions for a VDF. And now that we have sort of these core hardware primitives, both on the evaluation side and the proving side, is that we're going to be looking at some of the other various VDF constructions to see if they have better properties than the RSA VDF that we initially investigated. And one that's quite interesting here is snark-based VDFs, because if you were to create a snark-based VDF and hardware around that, that hardware could be used to accelerate other sort of zero knowledge proof generation, which would clearly be a benefit for both privacy and scalability purposes in the blockchain ecosystem. And furthermore, these snark-based VDFs also can reduce the complexity of the trusted setup process, which is something we'll hear about a little bit more. And then finally, sort of once we've completed the design and decided exactly on what sort of VDF we'll be moving into production, the Alliance will be looking to actually tape in a prototype ASIC. This will likely be done through what's called a shuttle process in semiconductor manufacturing, where basically you're able to share a part of a manufacturing lot or a part of a wafer and do a trial design to make sure that everything's functional on the chip. So this is just a little bit about where we'll be heading in the next year or so. And if anyone's interested, certainly feel free to check out vdfresearch.org or reach out to me if you have any questions or would like to participate. And with that, thank you, and I will pass it off. I guess we'll go to questions briefly, and then Mary will talk a little bit more about groups of unknown order.
Thank you very much, Kelly, for a great presentation. So I see we have a few questions in the chat. The first one from Ida Tucker was asking if you're increasing the evaluation speed of the slow user, why it does not increase also the speed of the fast adversary, which would then mean that the Amax is not improving.
Yeah, that's a great question. So the key thing here is that the attacker speed is basically an assumption, right? So we have to make some assumption about how fast someone can possibly go. And so that attacker speed point is relatively fixed. So for instance, in the case of the RSA VDFs, we make some assumptions about the attacker will only be able to compute one modular squaring per, clock cycle, and they're only going to be able to run at, say, 10 gigahertz max, right? If they've got a super, cooled custom silicon. And so you make an assumption around exactly how fast that attacker will go. And then the goal is, through algorithm and hardware development, that you basically provide hardware or make available hardware that gets the average user closer to that. And so in this case, what this means is if you assume the attacker is, say, using an ASIC that's running at 10 gigahertz, if we want to reduce that speed, what we want to do is we want to make available, say, an ASIC that's running at 5 gigahertz to the average user. And so that's really the key thing is we make some assumption about how fast the attacker can go. And that is one of the security considerations when constructing this is, are they running at 10 gigahertz? Are they using a normal silicon process? Are they using optical computing? There's all sorts of considerations when determining that. And there's quite a bit of research here on both the sort of semiconductor and exotic material side, as well as some more foundational research on the arithmetic and cryptographic side around the lower bounds of doing a single one of these operations. And again, there's some more information on these lower bounds on the VDF research site.
Thank you very much. So we have a second question from Ignacio Cascudo. He's considering applications such as randomness generation, and is saying that since VDF induce an inherent and unavoidable delay, what would be the advantage with respect to using a verifiable random function or a publicly verifiable secret sharing?
Yeah, I think it's a great question. So, and I'm not exact expert in some of these things. I think one of the main benefits of verifiable delay functions is that they are sort of asynchronous. So some of the other things like, that do verifiable secret sharing require sort of like a synchronous committee of folks to combine shares and get a result. And one of the nice things about the verifiable delay function is sort of purely asynchronous. So just, people can sort of compute this offline and then provide the proof into the system that everyone can verify. The other benefit of this over some of the other randomness schemes is that you only require sort of one person to compute the VDF. So if for some reason, all of the, most of the internet goes out and you lose that committee in a publicly verifiable system, or you get below the threshold, then you could have some liveness properties with the delay function. And where the verifiable delay function, you only need a single user to be online basically and produce that delay.
Okay, thank you very much. There is one last question from the chat from Dimitri Kolonelos, asking if the ASIC is designed specifically for computing G to the T between braces, or for G to the X in general.
Yeah, so the ASIC as designed just does a single round of modular squaring, and then it's sort of an iterative process, right? So the output will then get fed back into the input. So one of the security questions around it's sort of around the sequentiality of that process. So if you were to cube something or take it to the 5th power, can that be done in less steps than just doing 5 individual squarings? So far the belief is that it is an inherently sequential process, and that the lowest building block really is the squaring. And so the ASIC has been designed specifically around modular squaring. And as mentioned, it can support a wide variety of sizes of moduluses, anywhere from 256-bit up to 2,000 or even 4,000 bits. But the squaring is sort of the core component of the ASIC design.
Okay, thank you for the very clear answers. I guess I have just one more question before we hand it to Marie. So you mentioned that you, at the VDF Alliance, you made a new algorithm for modular squaring, which works in log K, with K being the size of the modulus. So I guess my question is the following regarding, so if you look at some crypto papers, they will usually stop at the level of the modular squaring, saying that you cannot basically break the VDF, meaning that you cannot compute it faster than the number of step T modular squaring, and then they would reduce that to some assumption based on RSA. So I guess my question is the following: is that a lower bound, the algorithm you found, or is there some work to find some lower bound to kind of have some security assumption or security proof of some kind regarding this low-level hypothesis?
Yeah, absolutely. So there is some work that's being conducted by Ryan Williams at MIT, who is actually looking at what is the lower bound in terms of gate depth. So how many gates do you need for, say, a 2,000 bit squaring? And so, it is believed that this algorithm, is certainly approaching that lower bound. Obviously, there are questions around, constants and that sort of thing here. But it is believed that that's, sort of close to the lower bound, and that is an active area of research. So yeah, great question, and it is an active area of research.
Okay, thank you very much. So I guess now we'll hand the floor to Marie.
Thanks.
So as Kelly mentioned, one of the things that we're wanting to do when it comes to building VDFs, well, one of the options is to use an RSA group. And the big challenge when it comes to RSA groups is that we need to somehow generate these RSA groups. We can't just do a trustless setup or a public coin setup as you could for other forms of VDFs. So RSA groups, I'm calling them this after the RSA encryption scheme, which would basically be a scheme where you have 2 prime numbers, P and Q, they're usually called, with a very high number of bits, say 1024. And here we have that it is very easy to find some modulus which satisfies these requirements, so some n, which is equal to P times Q. But given n, it is very difficult to go the other way around and to factor P and Q. If we had such an n such that no person in the world was able to compute P and Q, then this would give us an option for generating a group of unknown order, and therefore a VDF. And there are some advantages to using RSA groups over maybe other schemes, the big one being that they are very well studied. So RSA encryption, at least, has been around for decades. The idea that you can do time lock puzzles and such based on RSA problems has also been around for a long time, albeit perhaps less well studied than RSA groups themselves. They've been used in practice. We have lots of standards around them. Like when it comes to factoring, this is probably one of the things that the cryptography community understands best. Another sort of big advantage of, I would say, both RSA groups and class groups here is that we do have some very efficient algorithms for computing verifiable delay functions, assuming we have a group of unknown order. And Kelly sort of mentioned both these works earlier as well. One of them is by Benjamin Veselowski, and the other one is by Pietrzak. Sorry if I pronounced that wrong. And in both these schemes, it's fairly efficient to prove, it's fairly efficient to verify, the proofs aren't too large, and it's very difficult to get that if you're using other schemes. Another thing worth mentioning is that the hardware for RSA, while potentially more difficult than Sloth, is going to be much, much easier to produce than the hardware for class groups, just because the operations are that much simpler. When it comes to these groups of unknown order, so the number of bits you would need to use for the VDF would be higher than the number of bits that you need for RSA encryption. The reason being is that there are some attacks that work on VDFs which just don't work on encryption, which came out in the past year. The big reason, I think, being that we now have a motivation for people that do cryptanalysis to look at these problems in much, much more detail. Likewise, when it comes to class groups, there has been some progress specifically on class groups, which says that some class groups are not secure, but this is by no means a generic result. There are still plenty which are. So before I said that it is easy to compute an RSA modulus, n equals p times q. And this is true for encryption, because encryption, there is a single party who is generating that modulus. But when it comes to groups of unknown order, where you want anyone to be able to compute that modulus, this is no longer true. So if a single party were generating this modulus, what they would do is they would first generate just a random number p, which may or may not be prime. And they're then going to run a primality test. This primality test is not perfect. There is a very, 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 very small chance that the number they've generated is not prime, but it passes the test. But that chance is so low that you can consider that for cryptographic purposes, it's fine. So if it passes the test, then you accept that p is prime and you move on. But if it doesn't, then you just generate another number. Then you do the exact same process for generating your second prime q, multiply them together, that is your modulus. And we know that the number of candidates we're going to need in this situation, so the number of p and the number of q, is approximately ln p and ln q for the size of p and q that you want. When it comes to generating these inside an MPC, I'm actually going to tweak the algorithm a little bit for technical reasons. And rather than generating p and q separately, we're going to generate p and q at the same time and then test if they are prime at the same time. And this has the disadvantage being that you need to generate many more candidates before you can assume that you will find a success. But it also means that we have better ways of testing for primality inside a multi-party computation. So the problem with the primality test, the reason why it doesn't work in general, is because you actually do need knowledge of p and q in order to be able to conduct this test. So if someone were to just generate a random n and ask, is this an RSA modulus? We don't really have a good algorithm for testing that. That doesn't mean that one doesn't exist, but currently we don't have one. What we would like to do, considering the fact that we can't just generate a random n and test if it's a biprime, is what I sometimes say, or not, is we would like to instead run a trusted setup, which in some ways is like the next best thing. So you have many, many, many parties, and they all get together and they run this algorithm together. And then provided one party is honest, you should have it that nobody knows the factorization of the modulus, and you can test whether the modulus is actually biprime or not. similar to SNARK ceremonies, in that, we want to have many people contributing to that trust pool, but it is not the same algorithm that we're running. And in particular, in SNARK ceremonies, you would be looking to compute something of the form g to the x. But you don't then need to be able to extract out x from that computation. So this means that there are tricks we can do which are very efficient and very simple in order to make that ceremony an easy process. Whereas here we do actually need to, at the end of it all, be able to extract n from the computation, which means that we cannot use the same tricks. This doesn't mean that we shouldn't be learning from SNARK ceremonies, because there are, this is one of the few situations where we have had a ceremony run in practice where we can see things that have gone well, things that have gone wrong. One thing that certainly we have learnt is that you really want to have as many participants as possible, not only for a matter of making it more likely that your parameters are secure, but also for convincing other people that your parameters are secure. So you're going to want participants from all walks of life. You're going to want some from companies, some that are maybe anonymous, some which are just individual people. And ideally, you would like some people to be happy to publicize their involvement. It doesn't have to be everyone, such that you can sort of make it clear that this has been a transparent process where anyone can get involved if they want to. Another big important thing is you do need public verifiability. You can't just have it so that 100 people get together, generate a modulus, and then you say, here's the modulus, everything went fine, because then that is very difficult for anyone that wasn't actually involved in that process to see what happened, and again, to be convinced that everything was done correctly. The Ethereum Foundation collaborated with a team from Lahore for a long time, for about a year, when it came to designing a specific ceremony for RSA. And the Lahore team came up with a really, really nice solution. So this solution, it scales to thousands of participants, which before that, all the literature was not getting anywhere near that level. And they managed to come up with a full security proof, which is universally composable. And when we did some internal audits, we didn't find any problems. In general, we were very happy with how things are done. And the big nice thing about this scheme is that if any one of those 1,000 participants is honest, then the modulus is okay. However, the paper that we have so far is just a theory paper. And when it comes to moving that theory paper to practice, there are some big sort of things that we need to get right. And I should sort of say here that really nobody has managed to do, there's been very few MPCs which have been produced in practice with people running them in practice, such that we can sort of use that as a go-to for this is how it's done. This has very much been a learning curve that we've been figuring out as we've been going. But we do know that we want the security model to accurately represent the real implementation. If it doesn't, then our security model, well, our security proof doesn't mean anything at all. The other thing that we really need, which is maybe less important when you're talking about a theory paper, but is important when it comes to implementing something, is we need all parts of the system to be very well documented. And this includes sort of things that maybe theoretically aren't that interesting. Maybe they're just a detail that that is sort of, you have to write out and you have to do, and no one's going to sort of publicize the work as being sort of great and new. But without it, it becomes, you know, there could be small errors that get through. And because this is such a high trust system, even a small error can cause quite big problems. And similar for the code, that needs to be well documented. When it comes to the security model, there were many, many good things about the Diogenes security model that we would really like to keep. The big one being that it's actively secure. And this basically means that if a party diverts arbitrarily from the protocol, you can still know that everything's fine, that the modulus which is being produced is okay. Likewise, we have identifiable abort, which means that if some party does decide to cheat, then well, first of all, you can tell that they've cheated. This is public verifiability. And therefore be there like, okay, this modulus, it's not okay. We're going to run the protocol again. And because you know who's cheated, you can then not include that party in the next run of the protocol. And the other big thing is universal composability. And this basically means that the protocol can be used as a drop-in replacement for if you had a trusted party generate that modulus without changing the security, which you would then get in the resulting VDF. But one thing that we got wrong is that the security model is very much assuming that all variables in the system are independent, or all the pre-committed variables, I should say. In the real implementation, though, this was not true. There were variables which were being modeled as independent, which were actually dependent. And what the Zengo team found is they found that because there was some randomness being revealed by the players in order to improve efficiency, that randomness could then be used in order to compute other secrets which you weren't supposed to be able to know due to the fact that these variables were correlated. So obviously this is a big, big problem, and we do not want to make that same mistake again. And here is actually something where I think there wasn't really anything necessarily wrong with the security model, but there was potentially something wrong with our methodology when it came to how do we make sure that our actual implementation is representing that security model. And I think the big, big thing that we would need to do differently is we need to make sure that every piece of randomness which is supposed to be independent is actually independent, that we don't take any shortcuts in that particular area. And this does come at some cost. Like, because where before the variables were very correlated, there were lots of tricks you could do in order to make the proving time faster, or the MPC time faster, because you could basically do some batch computations. And like, if any of you have ever tried to implement multi-exponentiations, for example, you'll know that implementing 100 exponentiations at a time inside a multi-exponentiation is much, much quicker than computing one exponentiation at a time. So by keeping everything independent, we do lose some of the efficiency. Ideally, we'd still like to be able to scale to the same number of participants, however. So then there becomes a question of, are there any other optimizations we can make which are cleaner, which are not going to interfere with how we're generating these variables? And one of the big directions which myself and Dimitri have been looking at is we've been looking into whether we can replace the Primality Test. So the test for checking whether or not your modulus is actually equal to 1' times a second prime. So we've actually been looking at a very, very old primality test called the Fermat test, which has always been kind of discarded when it comes to a primality test because no one's been able to, well, really prove the security of that test. However, when it comes to actually finding a number which passes the Fermat test and is not prime and has been produced randomly rather than sort of you've concocted it using some fancy method, it turns out it's very, very, well, we haven't been able to find an example of a case where that's happened for larger numbers. So then we sort of ask ourselves the question, is this maybe more efficient than people are giving it credit? Because if it is, then it makes it much easier for us to generate a small number of candidates, much easier for us to generate our zero knowledge proofs. And the result of this is a much simpler and a much faster protocol. There are other challenges which I'd say are more general when it comes to moving an MPC protocol from theory to practice. And one of the big ones I noticed and I say this because I'm someone that comes from a zero knowledge background, so it's something I was really looking out for, is typically when you're moving from a passively secure MPC, where if all parties follow the protocol, then no information is revealed, to an actively secure MPC, where even if people don't follow the protocol, no information is revealed. What people will do in these theory papers is they'll say, apply a zero knowledge proof. If you prove in zero knowledge that you've behaved correctly, then this is enough for you to get an actively secure MPC, but only have to prove your passively secure MPC secure, which is a lot easier to do. And for an MPC theory paper, it is expected in some sense that you can treat this operation as a black box thing, because, you know, this is not really the focus of the work, not really the focus of the research, not really the focus of the improvements. And therefore, if you were to talk about exactly how do I achieve zero knowledge, that might detract from the paper in many ways. But when it comes to zero knowledge arguments used in practice, and for this I mean for a huge variety of applications, not just MPC, often when you're deciding what constraints are you going to use to accurately represent your problem, this is something where people spend a lot of attention to detail and a lot of effort to make sure they've got things right. Like a really good example of this, I would say, is the Zcash protocol specification, where they have an entire appendix, which is very, very long, describing each and every one of the constraints they've included in order to represent Zcash spend. And a Zcash spend is like a fairly simple operation compared to what we're trying to do here, like the computing hash functions and the computing commitments, and but they're not really doing anything outside of, I would say, discrete log operations or hash operations, which means that they can, but even with these simple operations, you're talking, you know, 20 pages of very detailed appendices where every single optimization has been proven. So when it comes to doing an MPC, we need to do the same thing. One easy way to get around this would be to have a compiler, I should say. Currently, we're unaware of any compilers which we would be happy using. Like, you need, in order to be working with a compiler, we need that it's gone through the same level of detail and auditing as you would if you had written out each and every constraint by hand. So because we don't know of that, maybe there is one. If there is, please let us know. We're then thinking about how are we going to design a system where we can write these constraints by hand such that we can still verify that they've all been done correctly. So when it comes to MPC, there are a few different ways, but one of the sorts of things you'd be trying to represent are ring LWE ciphertext, or just LWE ciphertext for that matter, or that oblivious transfers have been computed correctly, or that Palier ciphertexts are computed correctly. There may be others. Of those three options, the one that we're currently exploring and that we have high hopes for is the Palier encryptions. And the primary motivation for this decision is because we think that the Palier encryptions are going to be easier to represent inside a circuit such that we can run a zero knowledge proof than the other options. So we're currently looking at work by Hazy and others and seeing whether we can use our Primality Test and whether we can use other optimizations in order to scale this to many more parties. Again, here, there are places where we need to really be careful about the zero knowledge proofs. A big example is in the original paper. They are talking about encrypting Palier ciphertext, and for their encryption scheme, they basically say there exists a zero knowledge protocol for this. It was found by Kramer et al. Please refer to the original paper, and that's all they say on the matter. But when you actually sort of follow up this citation and have a look at it, you find that the zero knowledge scheme they've suggested only works when the public key which you're using for your PIA encryptions is generated using something called strong primes, but they don't test in the paper whether or not you're actually working with strong primes. And this is not necessarily a simple thing to prove. So when it comes to working with this paper, we again need to just look at those relations and say, is there a better way to represent these? Can we prove them more securely? Thank you very much for listening. I'm going to stop sharing now.
Thank you very much, Marie. So I don't see any question in the chat, but I've got a few myself. So you're insisting on the universal composability property, which I guess you.
I mean, I'm open to other models for sure.
Mm-hmm.
It's a good model. It's not the only model.
Yeah. So I don't know very well this area, but from the paper I've seen for the ceremony for the SNARK, they usually don't bother with universal composability. Do you have any comments on that?
It's less important for the SNARKs. Like, they're simpler. Like, really, the way I see it is there's sort of two main models that you might use when proving security. One is UC and the other is game-based. And game-based definitions are sort of very, very nice when you're proving a single protocol by itself, because you can really dig into the details. You can really find the areas where there might be mistakes. It's actually very good at picking up on bugs and such. But when it comes to like a bigger system where you're trying to find different building blocks that all fit together at the same time, this becomes something which you can do it with a game-based method, and I certainly have before, but it becomes more and more complicated the more components you add. You have to keep track of more things in your head. And eventually, I think it reaches a point where you're there like, is this simpler? Is this better? Maybe not.
Okay, right. I have another question which might be a bit naive. So you reminded us in the beginning of the presentation that RSA is one of the oldest public key cryptography. And I guess my question is, so you had to overcome quite a lot of difficulty to do this work. Are you surprised that these difficulties have not been foreseen, or is it something that people didn't want at the time to generate a modulus in multi-party computation?
I think people have been trying for years to generate an RSA modulus inside a multi-party computation. Certainly, I think there was a team at IBM which was trying to do it over a decade ago. But we have better tools now. We have better zero-knowledge proofs. We have things that are working in practice. It's sort of, it doesn't seem infeasible. But no, the fact that this is challenging, it's not surprising.
Okay. And so the zero-knowledge proof you're using, maybe I missed something here. So you need to do some zero-knowledge proof on the MPC protocol. So so you mentioned PIA encryption. So I guess you're not using general purpose zero-knowledge proof. You're using a tailored proof for PIA crypto system, or? We're
actually exploring both. So I mean, they both have their own challenges, I would say. There's lots of advantages to doing stuff inside a general purpose SNARK. But again, if we take that approach, then we really need to make sure that we can find a really nice way to represent those constraints such that we can, not only verify them ourselves, but hopefully get other people to be able to look at them, understand them, and verify them. So even if we take that method, we still need to make sure that we have a really clean way of explaining that.
Yeah, of course it's. I guess we have time for one last very quick question. So I do know that PIA has some generalization. Is it something that you looked at, and would that be interesting for your purposes? There is this scheme Damgard-Zurich, I believe, which is a generalization of the PIA crypto system. Is it something that you have looked at?
Yes, I'm aware of it. I don't know that it helps. It's a really nice scheme for sure, and if we could find a way to use it, then because it's pretty, I might be tempted, but I haven't seen an obvious way in which it's we should use that.
Well, if we don't have any more questions on the chat, thank you very much for the presentation. It was really good and a very nice insight on the complexities to put something into practice. Bye.
Thank you.
Thanks, everyone.